Okay, thank you very much, everyone, for being here today. I'm just going to look into a few ideas that we could basically think about in order to improve, hypothetically, the function of polymeric heart valve, given that they are not still in clinical use, but with a sort of a material perspective twist. So given that the most ideal polymeric heart valve is the one that would mimic native heart valves in terms of function, I think it is worthwhile looking into native heart valves and see why they are behaving the way they do from an engineering perspective. So if we look into native heart valves and leaflets, we will realize that these are made of materials which are very hyperelastic, so they're not just like spring. Mechanical properties will change as they deform. At the same time, they are very anisotropic, meaning that their properties change with the direction. So if you look at a pulmonary valve or an aortic valve, for instance, you would see that they are actually very stiff in the circumferential direction, while they are very soft in the radial direction. So that means that when they are under pressure, they actually wouldn't change in the circumferential direction in terms of size. They actually withhold the pressure, but they can be elongated in the radial direction to seal the valve. At the same time, we would see that these leaflets have a very negligible creep, but they relax under stress. What it means is that if you apply a stress on a leaflet, they tend to restructure internally and release some of these stress. So they dissipate energy. But at the same time, when we deform them or elongate them, they don't just keep elongating. So when they reach to a threshold, they just stay at that threshold. So what it basically implies is that after billions of cycles, the size of leaflets doesn't change. And at the same time, they can dissipate energy. So they don't really fracture or there's no stress concentration, for instance. So the reason for such a complex mechanical behavior is that leaflets and heart valves are heterogeneous at their core. So if you look at, for instance, leaflets, we know that they are made of different layers. And depending on the position of these layers, we would see that not only they have different compositions, but also if there are, for instance, any collagen fibers, they are aligned in a certain direction. So if you look at, for instance, the aortic leaflet or pulmonary leaflet, we would see that the layer which is facing the artery is rich in collagen. The layer at the opposite side is rich in elastin. The layer in the middle is actually a swollen network, basically like a hydrogel. At the same time, this heterogeneity that we see in the leaflets, it actually goes over a wide range of length scales. So it starts actually at sub-millimeter scale, sub-micron scale, rather. If we look at the sort of 10 nanometer, 100 nanometer size, you will see that these are made of collagen fibrils, which are made of oriented collagen fibers overlapping, collagen molecules overlapping with each other. So they are already anisotropic and heterogeneous at that level. Then if you go to the collagen fiber, which is made of these collagen fibrils, we see that they are actually made of oriented collagen fibrils as well. So they are already anisotropic at that level. And then when we go to the next stage, which is sort of sub-millimeter, a few hundreds of micron, you would see that in the leaflet through the thickness, these are made of different layers with different compositions. But the part which is even rich in collagen fiber, as I mentioned, the collagen fibers are oriented in the circumferential direction. So we have basically heterogeneity in terms of composition, and also we have anisotropic properties because of the alignment of already sort of anisotropic collagen fibers. So this whole thing actually leads to a material or a sort of a tissue which is highly anisotropic. But at the same time, even though we have a range of sort of wide range of length scale heterogeneity, these compounds are highly coupled with each other. So they actually work as the same material synergistically. So if it actually travel across the length scale, we don't see any sort of non-linearity in terms of stress. So there's no stress accumulating in tissue. That's a very sort of a complex tissue. So that sort of complexity leads to anisotropic properties at each layer of the leaflet and also the leaflet as a whole. So it's basically a very complex system. If we look at native heart valves and we want to sort of compare them with other materials and see how they sort of sit with other materials, we can look at two important parameters. So the x-axis is stiffness. So we go from very soft, sort of brain-looking material all the way to glass, which is at the end. And the y-axis is fracture energy. So that's a measure of how, for this is specific actually, measure how crack can propagate in material if there is a crack. And we go again from glass, which is very sort of brittle, all the way to things like stainless steel, which is very tough. So we have brain, which is a sort of a fatty kind of material tissue that will break. We will see that native valves actually have stiffness very similar to most elastomers that we use in everyday life, so like a rubber band. But they're not actually very tough. So 100 joule per square meter is not really a tough material. And if they didn't have this repair capability, they would have failed. Comparing them with the polymers that we use to make polymeric heart valves, we see that they have the same sort of stiffness. So they have the same sort of modulus. That's why they actually behave like a native heart valve, because they can deform and move. But they are much tougher, and they must be, because if there is any crack, they would fail. There's no way for them to repair themselves. At the same time, if we look at materials that are used for making mechanical heart valves, we see that they are absolutely stiff. And this is the reason why mechanical heart valves are made the way they are. They cannot motion the same that the native heart valve can do because they're so stiff. That's why we are making sort of tilting gates and things like that. These materials cannot really move the way polymers and native valves do. All right, so we know that the overlapping between the stiffness of polymeric materials and heart tissue is good. That's why we are interested in polymeric heart valves. And there has been some endeavors actually over the past few years. There are only a couple that made it to the first human trials, and we are waiting to hear about them in the next few years or so. But through the history, as they have been developed, the main focus point has been on the material to be biocompatible. So we have been thinking about material which could resist biodegradation, calcification, thrombosis, etc. So all these details that I mentioned about heterogeneity, which is at the core of heart valves and leaflets, and that's basically the reason heart valves open the way they do, close the way they do, pass the stress away from the leaflet to the body of valve, is because of the heterogeneity. This has been neglected through the whole concept that we have been looking at polymeric heart valves over the past many decades. All right, so there's quite a wide ground to cover when it comes to improving polymeric heart valves. I've divided this into three areas. One is just the geometry of polymeric heart valves. Given that polymers are easy materials to work with because they are processable at few hundreds of degrees compared to metals, which are thousands, we have a wide range of processing methods to use to make very complex shapes. So we have to remember that the shape of leaflets and wall would lead to distribution of stress on the leaflet. So designing more sort of novel and exotic leaflets and valves could help to distribute the stress on the leaflet and also away from the leaflet to the body of the valve. Also, we know that the orifice area is dictated by the shape of the leaflets and the valves. So we could include that into the design from the beginning. At the same time, we know that the flow pattern assists with opening and closing. So there are evidences that the actual pattern of flow around the leaflets would help with closing of the valve. And this is something that we could include in the design as well. In terms of material, we need to separate surface and bulk. So up to this point, the way we have looked at polymeric hard valves was using the same set of criteria for the bulk as we use for the surface. And this has restricted our access to the library of materials that we could use because we had to satisfy both bulk properties and also surface properties. But if we separate and decouple these, then we would be able to look into more sort of specially designed materials that would satisfy fatigue requirements, might have self-healing properties without worrying about the surface properties, because we know that we could then improve that via modification, etc. In terms of nanostructure, this is something that has been also ignored as well. We have to remember that these sort of nano and microstructure on the leaflets would lead to sort of better energy dissipation and at the same time the heterogeneity. So what I'm going to do for the rest of this talk is to just look at the heterogeneity mainly, because this is a topic that has been less explored in this context. So just for polymers, we know that we could introduce heterogeneity into polymers by aligning molecules at the molecular level. We know that we could apply certain processing conditions and sort of have some specific chemical structures that would lead to orientation of polymer chains. At the same time, at the micro and sub-millimeter scale, we could look into addition of some materials which are either one-dimensional or two-dimensional, such as sort of nanofibers or sheets, etc. And these would align as we process the materials, and that would lead to heterogeneity as well. Also, there are some certain fabrication techniques such as electrospinning, melt electrospinning, etc., that we will hear about these today, and that could lead to also a certain alignment and heterogeneity. And there's a novel sort of concept as well, which is the topological networks that I'm going to focus on. And these are networks that actually are heterogeneous at the sub-millimeter level, and that leads to absolutely extreme toughness and anisotropic properties. So starting with the simplest way, for instance, the most straightforward approach to introduce heterogeneity into materials and into a polymeric material that would lead to anisotropic properties. We know that we can orient macromolecular domain because of the size by applying certain stress regime and temperature regime. And one of those is a shear stress. So we know that polymer chains line in the direction of flow if they are under shear stress. So one of the processing techniques that includes high shear stress is injection molding. So there are some examples of injection molded polymeric hard valve where we have a mold, and in this case, the net actually enters the mold from the top. We have a distribution of shear and velocity, and that basically leads to orientation of polymer chains. As you can see on that leaflet, this is actually an experimental sort of result that you could see, that polymer chains are aligned in the direction of, in the circumferential direction towards the top, and in the radial direction, basically facing audience at the bottom. The outcome of that is obviously an anisotropic mechanical properties. So sort of what we are after, but there are two problems. And one is that these anisotropic properties are opposite what we want in some cases. We want to have basically circumferential alignment all the way. And two is that the polymer chains are very mobile entities. They actually don't just hold the oriented structure. So the first problem could be sort of addressed to some extent by changing the design of mold and sort of optimizing the way the melt enters the mold, having different temperature profile, etc. But the second problem could be addressed by chemistry. So most polymer chains that we use, they are elastomers, so they move. They are not just fixed in the space. When they're oriented, they would lose their sort of conformation. They actually renew it every few seconds or minutes even. So we need to have some strategies in place at the molecular level in order to be able to maintain that orientation of polymer chains so that they could lock in the orientation of chains after they are sort of aligned. One approach is by incorporating certain ligands into the backbone of polymer. After they are oriented, these could interact with each other to form either permanent or very strong sort of temporary bonds or crosslinks, which are strong enough to resist the tendency of chains that want to coil back under sort of temperature that they are being used. So as chemists, we know what sort of ligands actually we have access to. So this is not something that is unknown. We could actually go and pick the right sort of species and perhaps put it on the backbone of polymer. And this is something that Mark maybe can then comment on that later on during the coffee break. But this concept is looking into molecular orientation at the sort of molecular level, leading to real sort of anisotropic properties at the macroscopic level, as we saw. But there are some issues, as I mentioned. I think the main one would be the control of the direction of anisotropic properties. The other way to look at this is to look at the other extreme of heterogeneity length scale and look at some newer concepts that came out over the past couple of years. And one of them is the topologically architected polymeric networks. These are very interesting networks with heterogeneity at the millimeter or sub-millimeter level and lead again to the same anisotropic properties that we are after. So what are these? These are very similar to conventional composites that we see. They're made of two different materials. One is a bit stiffer than the other one, very similar to conventional composites. And one of them, the reinforcing phase, has a periodic pattern. As you can see, these are aligned in one direction, for instance, very similar to some composites as well. There are two differences, or actually three. One is that these are all made of very soft material, unlike most conventional composites that we know. Two is that the resolution of these patterns is at sub-millimeter or millimeter level. So these gaps are actually 1 millimeter or a few hundreds of microns. The second main difference is actually the last part. The interface between these two phases is actually very broad. This is actually completely opposite most conventional composites. So we have an interface which could actually cover the whole second phase, meaning that these networks are completely merged inside each other. That's the main difference that they have with conventional composites. What it means from a mechanical point of view is that if there's a stress or deformation, if you travel from one side of this to the other side, you wouldn't see any non-linearity in stress. So it basically very nicely distributes the stress from one phase to the other phase. There are some other advantages too. So we can control the chemistry of these phases separately, the way they're made, and we could assign very specific role to each phase. So one of them could dissipate energy, the other phase could store energy, very similar to real leaflets. So what are these? There are two examples here, but this is just a concept, and I walk you through. The top one is a hydrogel-based material, very thin film. The bottom one is an elastomer-based material. They don't need to be hydrogel or elastomer. It could be, you could use the same concept for either of these, doesn't matter, as long as there are soft networks. As you can see, we have a soft matrix, which can be formed very easily. Within that, we have a stiffer network. At the top, we have blocks oriented in one direction. At the bottom, we have fibers sort of elongated. And then we have a very broad interface. So these at the top, in fact, the soft matrix is completely diffused inside the rigid parts. So it's just, they're completely inside each other. And the same with the bottom part too. So they are cured together, these two. So what happens is that not only we have the anisotropic properties, but because of the way they have been designed, the stress is now distributed over the whole length of material. So if you look at that one on the right side, there's a notch introduced into this material. And what you see is actually that a crack being stretched 360%. It doesn't propagate. All right. And the reason is those glowing yellow area are polarized light sort of showing this, the concentration of stress. The way these are put together, and because of the fact that they are completely integrated, means that the stress has been distributed over the whole length of material. Usually would have only a little bit of a dot at the crack tip. So in this case, we don't have that. And that means the stress that could be concentrated on one small point now is distributed over the whole material. This is very similar to what we expect from most leaflets, right? At the bottom, we have some sort of similar cases where there is a crack that you can see the crack tip. After 10 to the power of 5 times of cycling and 20% stretch, the crack actually doesn't propagate as well because the whole body of material is involved in dissipating energy while those stiff materials are storing the elastic energy. So they actually can go back as well. So they dissipate energy and returning back to the same sort of size that they used to be. So very interesting concepts that could be implemented for hard valves, especially because of this length scale. It is very easy to work at this length scale compared to controlling the orientation of macromolecules, etc. Now, just to bridge these two sort of heterogeneity length scales, there is another concept I just wanted to very quickly just go over, that is matrix templating. So in this case, they are using ice crystals and some small molecules to template a matrix, but it doesn't need to be necessarily, again, ice crystals, etc. This is just a concept just to show that how sort of orienting polymer chains at the molecular level and then the higher level could lead to a very heterogeneous and extremely strong material. So in this case, we have a hydrogel. Ice has been introduced, growing from bottom to top in one direction. That can be done actually. Producing these alignments, as you can see in the yellow box. But then there's a second templating process, and that is leaching the second small molecule out of this matrix. So we have actually double sort of reinforcing. We have one alignment in the direction of the ice crystals, and then the other alignment is the sort of a footprint of the smaller molecules that left this matrix. So see what happens now if you look at the mechanical properties. These are actually extremely tough materials. So for those in the field of mechanical engineering, they would see that this is quite a lot of stretch. This means that you have stretched the material 3,000% in one direction without failing the other direction is 900%. And the stress that they can go under is basically much more than what a leaflet can have. So techniques like this could actually bridge the whole length scale in terms of heterogeneity. So just to conclude, look, I think the main concept is, I think in addition to all the work that we've been doing to make materials which are biocompatible and strong enough to go through sort of billions of cycles, we need to also look at other aspects of heart valves and acknowledge that there are some other elements involved here, including heterogeneity, that could be one of the main reasons leaflets behave they do. They are not necessarily the strongest material or the toughest material, but they have been designed perfectly in order to distribute stress, in order to open in certain ways, close in certain ways, and also to pass the stress away from the body of the leaflet to the valve. And these are all because of their microstructure and the sort of anisotropic properties. We know that as polymer engineers, we can introduce some concepts like that. Some of the challenges would be how to sort of merge these with fabrication processes, but some of these newer ideas are relatively easy to replicate using the new processing techniques that we have access to. So with that, thank you very much. Just acknowledge the funding and the school. Thank you.